Please be welcome to our today's webinar. In the upcoming minutes, I will explain you the basics of humidity, its interaction with materials, and how thermal analysis can help to identify the characteristic of these interaction. However, before I start with the main part of this talk, please let me introduce myself to you. My name is Michael Schöneich. I'm working as application scientist in the application laboratory of the company NETZSCH, which is situated in a small town in the northern of Bavaria in Germany. I have a thermoanalytic background of now more than 7 years and working since 2013 for the company NETZSCH. The company NETZSCH itself is a family-owned company consisting of 3 main business units: the pumps and system unit, grinding and dispersing, and finally the analyzing and testing unit, which I belong to. We produce analytic instruments to characterize the material behavior and the thermophysical properties in dependence of temperature. This means we build up different kind of analytic instruments to measure, for instance, dimension change, mass change, or phase change of materials in a wide temperature range, but also thermophysical properties like thermal conductivity, specific heat, and also thermal expansion are properties which can be analyzed with our instruments. So far to the company NETZSCH and your presenter. Now I will head over to the main part of this talk, which is the thermal analysis in connection with humid atmospheres. Here you see now the agenda of my talk. So I'll start with a little bit of daily life contact. So humidity in daily life, where have everybody of us already been in contact with water atmospheres surrounding us, and why this may be important to know this interaction. Then we will head over to a small theory part on the theory of humidity, which will finalize with a definition part. So we will give some basic terms like, for instance, dew point and relative humidity. And finally, we then come to the thermal analysis under humid atmospheres. I will explain or present you some methods of the thermal analytic in the field which can be combined with humid atmospheres and what properties can therefore be analyzed from the materials. And of course also some applications, so you get connection maybe with your typical day work. So let's head over to the first part, humidity in daily life and why it's important. I will start with just an easy claim that everybody of you has already been heard terms like humidity, dew point, or even relative humidity, because they all describe water content in a surrounding atmosphere, and this water content is one of the major parts which is influencing our climate. So at least if you had heard or seen the weather forecast, you have maybe also read or heard these terms like dew point and relative humidity, because they are the reasons why we have clouds or white rains. You can even test it by your own, that all of us are surrounded by water vapor. If you take out a bottle of water out of the freezer in a hot summer day, you will get immediately water drops on the cold surface of this bottle, and these water drops are just a result of condensed water vapor from the atmosphere. If you are unlucky and not at a warm place right now, you can even test it in colder places, but not with a bottle of water. You have to take your car, and if you get to your car in the morning, your windshield is normally frozen or covered by a layer of ice, and this is based on the same process that you have condensation of water vapor during night, which freeze on your windshield. So hopefully you see we have an atmosphere which is filled up with water. We can't see it, but it interacts with us, with our atmosphere, and also with our materials. And this interaction can occur in 2 different kind of possibilities. There's a physical interaction, which means we have physical processes like water absorption, which leads to expansion of materials, for instance. Or you have a chemical interaction. Chemical interaction means your substance or your materials really reacts with water in forming new compounds. One of the most prominent examples for this one is just the corrosion of steel. So we have an interaction. This interaction have every time also a result, and in case of material properties, these results is mostly a property change or at least an optical change. In case of property change, we can take again the example of corrosion of steel. So you have high stability of iron or steel, but if you corrode it to iron oxide, it's maybe broke in its parts. So for instance, if you have a completely corroded core, you don't want to drive with it anymore. From appearance side, we can take, for instance, a look in the polymer industries. If you have inject molding process and you take a raw material with a too high moisture or humidity content, you will get the so-called silver or humidity streaks, which just makes the appearance of your product not nice anymore, but in case of stability it has not so much influence. You can even test these property or appearance change by your own. You will take some foods at home and just let them stay some days. They will also interact with the atmosphere, with the water. In this case, they will release water to the atmosphere because they have a higher water content than the surrounding gas. So they will lose water, they will shrink, they will don't look any more nice, and also the property, the taste is not the same anymore. So hopefully from these few examples you understand that the water content on the air or on the atmosphere has a really high impact on material properties, either physical or chemical way. And we need to understand or at least to identify these interactions. And thermal analysis is one of the possible parts, but before we can start with these methods, we need to understand how this water vapor is produced or where it comes from to understand how we can perform our experiments. And therefore, we will head over now to a small part of theory. And I want to start with just the imagination that you have water, liquid water. In this liquid water, you have water molecules, HO2, and these molecules are bonded to each other by so-called intermolecular bondings, or in more precisely name, it's a hydrogen bond. These hydrogen bond hold all the molecules together, and in finalized, as easy said, they build up this liquid water. Each of these molecules has its own energy inside of this. There is a distribution, not all the molecules have the same, and this distribution can be given as shown here with the Maxwell-Boltzmann distribution. In this distribution, it's the important part on the higher energy range, as some molecules inside of liquid and water have really high energies which even exceed the energy which is used or which is defined by the hydrogen bonds. This means these few molecules are able to even break this bond. So in the case these molecules have this high energy content and they are on the surface of water, liquid water, then there is the possibility that they are removed from the liquid state and go into the gaseous state. This process is called evaporation. So they form from a liquid water the gaseous water. There's all the other way around, so we can also go from a gaseous molecule which hits the surface of the liquid water, which can be, let's say, catched by the liquid molecules with the help of the hydrogen bonding. So we have in a system based out of evaporation and condensation, both processes at the same time. And if we close the system, then we have an equilibrium state. This means after a certain time, the system will come to a constant rate, which is the same for evaporation like for the condensation. And finally, in this case, you get a defined water atmosphere, gaseous atmosphere above the liquid water. This state is called equilibrium state or the saturated state, as the gas phase is saturated with water. For the further explanation, this state refers to the so-called 100% relative humidity. What this relative humidity really means we will see also in the definition part. However, you see that this part or this concept is working for a constant temperature, because this whole process of evaporation and condensation is highly temperature dependent. Please remember back to the energy distribution. All the molecules have different kind of energies, and if we increase the temperature, also the energy of the molecules will be changed and also increased. So the Max-Boltzmann distribution will just change its shape. And as we start at higher temperature, more molecules exceed the energy limit of this hydrogen bond, which just means there can be more molecules leave the liquid state and evaporate. If we go for a practical display of this one, then we have this graph here. So you see here the amount of water content in the gas phase versus the temperature. And this is just the shown practical example of this theory part with this closed system. This means at 20 degrees C we have a saturated water amount above the liquid state of 1 cubic meter, that is 17.3 milliliter pure water on 1 cubic meter of gas. If we increase the temperature, this amount of water will also increase because of the higher energy in the liquid state, increased evaporation rate. So that we at really high temperature of liquid water, which is about 95 degrees C, have almost half a liter of water inside of the gas phase. So based on this short theory part, you hopefully understand that the evaporation or the gaseous water is caused by evaporation and condensation cycles. These cycles get to a stable system, which calls the equilibrium state or saturated state, and this whole complex is highly temperature dependent, so that the amount of water in the gas phase is changed with the temperature. From this part, we will now head over to the definitions, which we will need to use for the characterization of our final experiments, which we want to use in the thermal analysis. The most prominent definition term is the so-called relative humidity. It's the ratio of water content to a maximum water content at a given temperature. Here it's important that it must be stated together with the according temperature, otherwise it's meaningless. Hopefully you understand the second sentence already. As shown before, the water content, the maximum water content, which is the reference for the relative humidity, is highly dependent on the temperature, as seen in the graph before. Therefore, we have every time to state it with the temperature. As example, again, you see here 3 volumes of gas at 20, at 30, and at 40 degrees C, and they have all the same value for the relative humidity. However, because the maximum content of water is different for 20, 30, and 40 degrees C, the absolute water content is also different in this case, as they have different kind of referring water content. However, there is not only the possibility to give the water content as relative humidity, you can also give it as absolute water content, also used as molar fraction. This term refers to the ratio of water molecules within a given volume with respect to the total number of molecules. In this case, we talk about something like a concentration. Again, an example, here we have the 30 degrees C with a relative humidity of 55%, and you can also give this relative humidity definition with the absolute values. In this case, it's 2.3% of the whole volume is water, and also as concentration, it's about 17.3 gram per cubic meter. Besides these humidity or water content terms, you have also the possibility to describe a humidity level of gas by the so-called term dew point. This is a little bit tricky. The dew point is the temperature which refers to a certain point of 100% relative humidity. To understand this, I have again this graph what we saw before, and here you have to think that you have gas atmosphere which is less than 100% filled with water, so it's not saturated. However, if you cool this gas volume down to a certain temperature, it will hit this 100% curve, which is shown in this graph. And at this point, the atmosphere or the volume is not able to handle the water content anymore. So it needs to decrease because at lower temperature, the 100% value is smaller than the actual one. And this temperature where the water will start to condense because the system needs to remove water is called the dew point. Practical way, we see it every time at the sky because it's one of the reasons why sometimes clouds have a flat bottom. It's the same principle like shown in the graph here. Humid air, which is not completely saturated, rises and cools down during its race upwards, and at a defined altitude it crosses this dew point line and water needs to be condensed, and therefore the cloud becomes visible. The final term has nothing to do with the gaseous phase anymore, it's the moisture content. This term refers to the quantity of water contained in solid materials like rocks, ceramic, foods, or wood. It can be given as volumetric or gravimetric content. Here the easy example is just that the moisture content refers, for instance, to the water amount which can be absorbed by a solid material. So now we have some terms, and with these terms we will now head over to the Humid calculator of the company NETZSCH. This one will help you to easily calculate all the relationships between relative humidity, molar fraction, and dew point, because I can expect all the things which I explained before is a little bit complicated to follow, and here we have an easy way for you to handle all of these kind of different terms and values, and therefore it's included in all of our current versions of our NETZSCH Proteus software. So even if you have already a NETZSCH system but without humidity attachment, you can have even this calculator inside of your software distribution, so you can at least test it. So now we have hopefully understand that humidity is all surrounding ourselves and all of our materials. We have interaction which needs to be characterized, and therefore we will now head over to methods of thermal analysis, and I will show you now in total 3 methods which can be used in combination with these humid atmospheres and what properties can be analyzed. First of all, I will start with the thermogravimetric analysis. The thermogravimetry is a technique in which the mass of a substance is measured as a function of temperature or time, while the substance is subjected to a controlled temperature program in specific atmosphere. So for us today, the specific atmosphere is an important point. So we want to analyze gravimetric, so mass changes of sample in humid atmospheres, and these humid atmospheres are produced by a humidity generator. This generator produces defined humidity levels by mixing up a wet and a dry gas flow. The wet gas flow, of course, is water, and the dry gas flow is typically nitrogen, argon, or air. This humidity generator from the practical side can achieve a maximum dew point of 80 degrees C, which refers to a water concentration between 0.1 and up to 47% in the complete gas phase. In case of we want to do or perform a thermogravimetric analysis, we connect these humidity generator with our STA 449F3 Jupiter. In combination with humidity accessory, this system can perform analysis up to 1600 degrees C, and it has also one special thing, which is an interchangeable sample carrier system that allows to use different kind of sample holders as plate sample holders, beakers, or even hang-down sample holders, and therefore you can analyze any kind of sample shape, if it's a bulk sample, if it's a powder, a foam, a plate, a fiber, or even a foil. To perform such an analysis, we see here on the next slide one example for this. It's the absorption of water of a polyamide 6 foil sample with a thickness of 250 micrometers. The sample was held constant at a temperature of 40 degrees C, and we performed some humidity steps of 0, 25, 50 and 75%. What you see in the green curve is the mass change. So on each change or each step of the humidity, we get a response from the sample as the mass increases. This means the sample absorbs water, and the moisture content, which is the property which we in principle determine here, increases with the humidity content of the surrounding atmosphere. Furthermore, so see also that we have a time-dependent process of absorption. It's not just a step-like change like the humidity profile. So we have kinetic influences which can also be analyzed. This means we can, for instance, determine the so-called diffusion coefficient of materials with the help of humidity setup. So thermogravimetric as standalone method is useful to at least identify that we have an interaction, in this case physical interaction, and we can even characterize it so we can get quantitative value of water absorption content. The next method is the thermomechanical analysis, or short TMA, a technique in which the deformation of a substance under a non-austolotic load is measured as a function of temperature or time, while the substance is subjected to a controlled temperature program in specific atmosphere. So again, for a specific atmosphere in our case, we use the already mentioned humidity generator, and for thermomechanic analysis, we will combine it with our NETZSCH TMA 402 F1 Hyperion. This setup is able to run up to max temperatures of 500 degrees C, and we have even two measuring modes, so tension and compression mode, so that you can also measure bulk samples in compression or fibers and foils in tension mode. To get a feeling what the TMA is showing, we have again the same example as shown under the thermogravimetric analysis part. So we have here again the water absorption of polyamide 6. It's the same foil sample. It's the same temperature program and humidity program. What you see is that we get also a response from the TMA. In this case, we measure the length change, which is caused by the increase of moisture content, which results from the water absorption of the sample. You see also that we can use it as kinetic analysis, as we have again the same kinetic procedure. Of course, it's the same process here. And you see that you have again a quantitative analysis of each step independent of the amount of humidity of the surrounding atmosphere. So thermomechanic analysis is also able, as standalone method, to identify and characterize the process. We are determining here the sample expansion as property. And what you see, for instance, here in this example, we have a starting length of a material of about 50 millimeters, and we have a total increase of more than 300 micrometers. So we have here really a significant length change, which is already influencing, for instance, the size of, for instance, possible products, shapes. So the third method is the dynamic mechanic analysis, DMA. It's a technique in which the storage modulus and loss modulus of a substance under non-austolotic load is measured as a function of temperature, time, or frequency of oscillation, while the subject is subjected to a controlled temperature program in specific atmosphere. So we have again the humidity generator and again a NETZSCH product, in this case the DMA 242E Artemis. Here we are limited to a max temperature of 200 degrees C with the humidity accessory, but we have also different kind of measuring modes, which are tension, bending and compression, so we are also able to measure different kind of sample shapes. The DMA, as already given by the definition, is measuring the so-called E modulus, which refers to the stiffness of a material. So here you see as example measurement again the polyamide foil, and what is here interesting, between the zero humidity level and the 75% relative humidity, we have a decrease of the E modulus of a factor by 5. So this means we have a high impact on the stiffness of the material during the water contact. So here you see a possible practical example that if you use this material to build up construction parts which has to be have a high mechanical stability, you get problems if you bring them in a surrounded with a high humidity level, because then the water will be absorbed by the material and the stiffness of the mechanical stability will dramatically change. From the method part, also the DMA is able to identify it as standalone. We see again the kinetic procedure of the change of the E modulus. So here we have also possibilities to do kinetic analysis. A summary of these thermal analytic measures, again a comparison of all three measurements I showed you before. So hopefully you see here that in principle thermal analytic methods are able to identify and even characterize the water absorption or reaction processes. Furthermore, all three types of shown methods are able to get in correlation to each other. This means we can get further interpretation possibilities from the point of doing all three methods on the same material. For instance, the TGA shows us that we have a physical interaction, so we have an increase in moisture content and not a decomposition reaction, for instance. Then the TMA and the DMA shows us the resulting property change as changing of the dimensions, so expansion process or change in the mechanic stability. So from this one, you see hopefully that thermal analysis is able to be used in conjunction with humid atmosphere, and that it's able to really determine, analyze the already described interaction between materials and the water gas. So finally, we will now head over to some more examples so that you see that it's not only limited for the now already shown polymer materials, we can even use it on a human hair. So here we have a measurement on a human hair, constant temperature 35 degrees C, different kind of humidity levels. So in principle it's a similar experiment like shown before. We see also that on this TMA measurement the hair is also changing its length. This process was previously used in these, let's say, analog hygrometers to measure, for instance, room humidity values, so climate measurements. In the northern days, these analysis of human air is maybe even more used in cosmetic fields, as you want to know how the hair of humans is reacting to different kind of climatic conditions and how, for instance, a shampoo can influence the reaction of the hair. So you want to have that your hair is smooth even under dry conditions. The next example comes from the inorganic field. It's here shown analysis of so-called cellulite materials. These cellulites are absorption materials which can be used, for instance, cleaning of gas flows or just water absorption in certain rooms or areas. What you see here as a test run is a double cycle of this material under wet gas flow and dry gas flow at constant temperature. So in the first one you have an increase in mass because we are applying a humid atmosphere on the sample. It will take up a certain amount of mass, so a certain amount of water, and it will increase its mass. Then in the dry gas flow it will be releasing this water again. So this is just the so-called activation cycle to test the maximum absorption capacity. And finally you can repeat these cycles several times to test the stability of the material. Here just shown 2 cycles, so we see after the first activation, which is slightly less, the system is relatively stable with a water uptake of about 26%. The next example comes from the natural materials, or let's say also construction of building materials. Maybe some of you have already asked themselves why the table of the dining wood table at home is cut in this way and not maybe in the other way around. And here you have a measurement on wood, and we have cut samples in the longitudinal range, so vertical, radial from the center to the outside, and tangential. And what you see is that wood has a high anisotropic property if we talk about water implicit thermal expansion. So this means if water is taken up by wood, the length change in the longitudinal range is about 0.1%, while in the radial range we are already in around 1%, and in tangential up to 2%. This means we have a factor of 20 in the size change between the different directions of wood. And therefore, if you want to construct something out of wood material, then you should cut it in the longitudinal range, because then the size of the construction part stays nearly constant even under changed in climatic conditions. So then we come to a final example for this webinar. It's in evaporation of tungsten oxide. This is the first example which is not showing physical interaction, as all the other before were just water absorption examples. In this case we are now at the second interaction possibility, the chemical ones. You have here two comparison curves. The blue one is the mass curve performed or measured without humidity applied to the sample, and the green one is with applied humidity of a dew point of 25 degrees C. What you see is that the blue curve is showing nearly no mass change, which means the reaction of solid tungsten oxide to gaseous one, so the sublimation process of this material, is nearly not present at the here shown temperature range of about 1000 degrees C. However, if we introduce in the system a small content of water, which is just this 25 degrees C dew point, then the solid tungsten oxide can react with the gaseous water to form the so-called tungsten oxide acid. And this tungsten oxide acid is highly volatile, and therefore it can be easily evaporated at 1000 degrees C. So here you see that we have really chemical interaction building up new compounds which have a completely different physical behavior than the previous one. And what we also can see from this experiment, if you perform this with different type of temperature steps, you get different kind of mass values per time. So the evaporation rate can be determined, and based on this evaporation rate you can, for instance, go also to a kinetic analysis of this whole chemical process. So with this example, I'm now at the end of the first part of the talk with the webinar. Hopefully I was able to show you that humidity is one of our essential property defining parameters of materials. So we have chemical and physical interactions which result just in property change of the materials. I have also given you some information about the basics of the theory of humidity. So I have hopefully explained for you that we have a saturated state which is defined by evaporation and condensation process, that this state and therefore also the amount of water inside of a certain volume is highly temperature dependent, and that this whole thing can be explained or characterized by the terms relative humidity, dew point, and molar concentration. From the thermoanalytic side, hopefully I was able to show you that thermoanalytic methods are a sufficient tool for characterize and identifies water-based processes. So with the thermogravimetric analysis you are able, for instance, to look at moisture content, mass changes, independence of humidity level. TMA allows for thermal expansion determination, the DMA for the E modulus, and all together can do also kinetic analysis like diffusion coefficient determination. There are even more possibilities which require some special conditions. So for instance, we can also talk about dielectric analysis, so cueing behavior and so on. With that, I'm now at the end of my talk. I thank you for your attention, and we will now head over to a question and answer part. Here you get now the possibility to use the question option inside of this chat or webinar software to ask questions which I'll try to answer in the, let's say, upcoming 50 minutes. So please use now this chat function. While you do this, I want to inform you that we have an upcoming special webinar, which is a video live stream on the topic of quality control on compounds. This will be formed as live video. So two of my colleagues will answer your questions live and will also use the video technique to, let's maybe say or show you some of the topics directly on our instruments. If you're interested in this, you can get more information on the here shown link. And I will also ask you that you please answer our short survey, which we'll send you afterwards by email. It will take only about 2 minutes and will help us to provide you with specific and high quality webinars that you deserve. So with that, we are now on the question and answer part. And here we have the first question. And the first question is, are there special instruments requirement for humidity application? Yeah, I have not shown all or discussed all every time called as humidity accessories and the temperature limit. So in case of our instrument, there are normally different kind of furnace options, and you need special furnaces to prevent the system for condensation problems, because if you have condensation inside of your system, it can also damage the electric parts and so on. Therefore, the special equipment for humidity is most time equipped with additional heaters so that all parts of the system can be held at a constant temperature, so you have no cold spots, which will lead to the condensation problems. So yes, there are special instrument requirements, but as I showed you with 3 possibilities, these special instruments require also taken into response. So the temperature limits, for instance, already refer to these special instruments. So we have here next question. What about the effects of pressure inside of a closed system? So if we talk about humidity, of course, you can increase the pressure, so the density of gas, and this will affect this evaporation rate, or more precisely, first of all, the condensation rate. So the pressure in the system is, of course, affecting also the humidity value. But if you remember the calculator I've shown you before, there's also a part or a value where you type in the system pressure. So this calculator I showed will also take these effects into account. So then I have a really long question here, and I must just read it before, so please give me just a half a minute. So we have here the first question about the DMA measurement. So there was a thin sample of PA characterized by tension mode, and I suppose that the sample is that thin in the order to get a relative fast water absorption. That is correct. We use this thin sample because if you use thicker sample, you can also do the same experiment, but it just will take longer. Then the next part is we want to know the correct deformations of amplitude. Unfortunately, right now I have not this information, but I will send it to you afterwards by email. And yes, the clamping, so you must clamp these foil inside of this tension mode holder is quite important. So you need a little bit experience, but in principle it's not the problem to do this. In addition, do you know what is the tension mode is recommended at this most? So yes, in case of foil sample, the tension mode is the best one to perform these kind of water absorption experiments in the DMA. Have you more bulky samples, then of course it will go to the bending setup. So it depends a little bit on the sample thickness. So next question, are there any minimum requirements on the weight of a probe to be tested? I'm thinking about analysis of examples of thin films, hundreds of nanometers on inert substances such as glass. So in this case, you have not really limits on weight of the sample. You are more limit in the signal of the sample. So the systems here has a resolution of about 0.1 microgram if we talk about the STA, and of course, we have some limits also in detection. So you need a certain amount of mass uptake, so water absorption, to really get a signal. In this case, the signal height is just depending on the sample weight. So we must just test it in principle. However, the substance can be subtracted on a class for easier handling. If you have really thin films and you want to do these further analysis like TMA or DMA, it's quite difficult to handle it. In the case of a STA or thermogravimetric analysis, there is no problem because the sample will just be hang down or lay on the plate or will be put in the beaker. But in case of the TMA and DMA, you must fit it inside of these sample holders, so we must be clamped, there must be a pre-tension a little bit. So here we get problems with too thin samples, so you must go with substances which are on substrates, for instance. So unfortunately I see no further question right now. Okay, yes, we have a new one. So DSC and TGA measurements under humid atmosphere. Within a reaction with vapor, energy is being released. The DSC results does not correlate with the corresponding TGA measurement, as it's usually why this does happen. Yes, so of course you can perform TGA and DSC at the same time, as the shown instrument was a STA. The TG signal is well determined, but the DSC signal is sometimes quite difficult because with the water in the atmosphere you have a high heat capacity, which allows the system to also take out a high amount of energy, and therefore you will normally get to lower values. This is just the reason, or just caused by the typical DSC setup. A DSC is a so-called open system. You have a gas flow which is purging the whole time through the system. To really get the high defined or complete equilibrium energy of these absorption processes, you would normally go to a closed system like calorimeter systems, where you did not have the exchange of the atmosphere. In this case, the atmosphere also will take up the energy of the absorption process, but it will stay inside of the system. So here it's mostly based on the difference that you have an open and closed system, and the open system is able to also transport some energy by the gas phase, which is then not further detected by the sensor. Then we have another sample. How is humidity controlled beyond the 100 degree C? For example, in the case of your shown Wolfram tungsten measurement. So yes, I have shown you that the humidity generator is maximum limited to 80 degrees C dew point. However, it's also referring to a molar or absolute concentration of water, which was given as 47%. So in this case, the water is not anymore controlled in thinking with this relative humidity context. You just work with these molar fraction. So in this case, we have defined a molar concentration of water inside of the gas phase and have used this for this experiment on the tungsten oxide. And this molar concentration, which was selected, was just referring to the 25 degrees C dew point. So then I see now no further questions. I will give you, let's say, 1 minute more to maybe send one. Otherwise, you see also our webinar email here. So if you get any question afterwards, you can also contact us via the email ngp_webinar@netzsch.com. So please feel free to just ask question afterwards. You can also get the whole presentation as PDF if required. From this point, no further question. So I would say thank you for your attention again. Hopefully this webinar was interesting for you. So, and maybe we see us in the next time on the next webinar on NETZSCH. So thank you and goodbye.